All right, I skipped exercise 2, and we'll go ahead and do that in class. So feel free to take some time to do that, and then we'll discuss the answers in class next week. And let's start here with exercise 3. A company makes cola drinks, states that the mean caffeine content per one 12-ounce bottle is 40 milligrams. So again, very important words here. We have that word mean is 40. We also have this sort of keyword of states, right? This is telling us this is a claimed value. This is likely, if we wanted to translate it in that way, sort of our mu naught, right? The claimed value that we're going to have in our hypotheses. We don't need to put the not in there, but just throwing that out there. Suppose you work as a quality control manager and are asked to verify this claim. So again, verifying a claim, having a hypothesized value, we're looking at a hypothesis test. We're not estimating the amount in these bottles of cola. We're seeing if it equals this amount that we're being told. During your test, you find that a random sample of 30 12-ounce bottles, we got our cool keyword of sample, has a mean caffeine content of 38.9. So since this word mean is in the same sentence as our sample, we've just got an X bar. We've got our evidence to prove that maybe the answer, the actual stated value of 40 is wrong. With a standard deviation, same sentence, so we're looking at an S. This is a sample value. And as soon as we have an S, we know we're dealing with a t-test. Though, as I pointed out, we'll always be doing a t-test. At a 0.01 level of significance, can you reject their claim? So there's our alpha, and we're looking to see if we can reject the claim. So, all right, so now that we have all of our information, we can see that we want to do a one sample test for means, right? We have one sample, we want to test versus a stated value for a mean, and we could set up all of our steps for this hypothesis test. So step 1, our hypotheses. Well, again, this is all about means, so we're going to use mu. They stated that it's 40, and we want to see if we can reject this claim. So our alternative doesn't say we think it's more than, we think it's less than. Don't get distracted by the fact that we have a sample that's less than. We just want to reject their claim. We want to show that it is not equal to 40, right? And the reason we have to do this is because as scientists, we're supposed to come up with our hypotheses before we get started. We can't let the data make our decision for us. Because if we take the sample first and get out this 38.9 and make it a left-tailed test, we're essentially going to cut our p-value in half for no reason other than the fact that we cheated. So this way our p-value will be twice as large, which is in line, though, with what our original hypotheses were. So step 2, we're going to go ahead and get our test statistic. And again, I'm going to go ahead and go to the formula sheet here. If you are doing this by hand, oops, I did not mean to erase that. Oh my God, I have so much stuff written on here. I got so excited by we're doing a hypothesis test for means, and as usual, we don't know sigma, so we're here. Okay, and remember, this was t interval, and so if you have the big calculator, you can do the steps 2 and 3 using t-tests. So if you have the big calculator, I strongly suggest fast forwarding until you see me pull out my calculator, in which time I'll do it. If you have a little calculator, I'm going to do all of the steps for you. So this is our formula, and it makes sense if you think about it. So let's go ahead and I'll write down the formula and I'll explain why it makes sense. So t is equal to x bar minus mu divided by s over the square root of n. So the reason why this makes sense is we're basically saying, okay, well, we got out 38.9 when we took a sample. Is that different enough from 40? How different is that from 40? Not very different. I'm just thinking out loud. And that's exactly what our test statistic measures, right? So here's what we saw, here's what we expected, and then we need to take into account how much variation there was. That's why we use our standard deviation of our sample mean. Remember, we're underneath all of this, we're using the 7.1, the sampling distribution stuff. So 5.5 divided by the square root of 30. If you're doing this in your little calculator, I wish I had it with me, you're going to want to go ahead and do that little fraction button first so you can have this look exactly the same. If you're doing it, what I would suggest, just use parentheses around your numerator so that way it does this subtraction first. Oops, I added 1. Great. It always does this to me if I press buttons too many times. And then also add a parenthesis around your denominator. If you don't have parentheses around this denominator, it's going to divide and then divide again, as opposed to dividing by a fraction, which is actually multiplying by that reciprocal. So 5.5 divided by the square root of 30. Hold on, my child apparently needs my assistance. Cool. So we get out a test statistic here of negative 1.095. And since the t-table doesn't have that rounding to 2 decimal places, we can go ahead and keep an extra decimal if we want. If we rounded to 2, I'm not going to be mad at you here either. And just as a heads up, we could also have drawn this out right. We expected the mean to be 40. We got out 38.9. And our not equal to means that we're not only looking for this tail, but also the tail equally above. All right, so step 3, oops, I wanted to keep blue. Sorry, I'm very inattentive about my colors, is we're gonna go grab our p-value. So remember, if we're looking for a p-value, we're gonna use this t-value in our t-table. So if we're using the table, we know we need our degree of freedom, which is 40 minus 1. And remember, we're going to do 2 steps. In this case, we're going to look up a positive because that's the best we can do in a t-table. And then we are going to times 2 because we had a 2-tailed test. So we're going to look on the degree of freedom is equal to 39 line for 1.1. Child is angry. All right, so just like the confidence interval questions, if we don't have the value that we need exactly, in this case we don't have 39 exactly, you're going to round down. Don't go to 40 because 40 is closest. You're going to go down to 30, and we're looking for 1.1. And you'll note it wouldn't have made a difference whichever line we were on, so we feel even better about that. If you had chosen 40, you wouldn't have been in trouble. And here's our upper tail probability. Pretty dang large, which makes sense considering 38.9 was really not that far away from 40, and a test statistic of 1.1, not that exciting. So we get out values between 0.1 and 0.15. You'll notice that they're not written in descending order, so I always reverse them. So 0.0, oops, that's not what, 0.1 to 0.15. But we needed to make sure we multiplied by 2. So our p-value is actually 0.2 to 0.3. Now, I'm going to do this with the big calculator. And remember, if you have the little calculator and you're going, holy crap, this would be so much nicer with the big calculator, you can borrow these for a week from the STEM Center in the library. So do that if you want to. Make sure you don't wait until test day to do it. Maybe check them out this week so that way you can get some practice with it beforehand. So big calculator, you're doing t-tests, making sure it says stats. We're going to put in our hypothesized value, which is why I used a mu naught when I first translated that. Our x bar was 38.9. Remember, the s, you're going to use the original one, not the divided by square root of n, so 5.5. And then our n was 30. And we were interested in a not equal to test. So everything's in there. Our mean value, what we got out is our evidence. Standard deviation, so we have some idea of a spread. The sample size, we have some idea of how much information we had, and our alternative. Calculate, we get out the exact same t or test statistic, and we get an exact p-value, which does fall within our range, but can be a little bit nicer for some students. So 0.2823. So either of these is completely correct for the exam. You can choose whichever you want, calculator or table, whichever is available to you. All right, so step 4, how does this p-value, either one of them compared to an alpha of 0.01? Either one is much larger, right? So in either way, we're going to fail to reject the null, which means our step 5 at a significance level of 1%, and hell, even at a significance level of 10%. So like I said, the significance levels are a little arbitrary and seem silly when they're set like this, because even at the loosey-gooseyest significance level of 10%, we would still not have enough evidence. There is not, because we failed to reject, enough evidence to reject the company's claim. And again, here I'm just sort of looking at that last line and making sure that it aligns with my alternative. We could also have said to show that the average calorie content, remember we should use that word average, but in this case, the claim was out there. The average calorie content, or no, was this amount of caffeine? A mean caffeine content is equal to 40. Is not equal to 40. I don't know, something. You get the idea.